Here is the second video in a two-part series on probability. This video is going to explore dependent versus independent events and also something called conditional probability. And rather than just coming out and defining what those things are, I think we'll look at some examples, and then as these topics emerge, we'll explain and define them carefully at that time. So first of all, in this example, we're going to flip a coin and roll a die. The first question is, what's the probability of event A? The coin lands on tails. Well, that's equal to 1/2. And that's because there's only one favorable outcome among two possible equally likely outcomes. Event B, what's the probability that when you roll a die, it lands on the number 5? Well, a die, of course, can show 6 different numbers, so there's 6 equally likely different possible outcomes, and only one of these is favorable. So that's 1/6. Now, if these first two examples bothered you, you should go back and watch the first video. I think it'll help. Now we have a joint probability. What's the probability that both A and B occur, so that we get tails for the coin and 5 on the die? We want both of these things. And this probability is not very high. In fact, it's lower than both of these because you're asking for two things that aren't very likely to begin with, and you want them both to happen. Well, here's the sample space. H5, for example, means that coin is heads and the die is 5. T3, of course, means the coin is tails and the die is 3. But as you can see, there are 12 different possible outcomes for these combinations, and only one of them is favorable. It's this one. So this probability is 1/12. Now, maybe it occurred to you, maybe it didn't. You can compute this by multiplying these two probabilities together. That's 1/2 times 1/6, because that makes 1/12. And that was just the probability of A times the probability of B. Now, can you always do this for a joint probability? No, not always. You can do this any time that you have two events that you know are independent. What does independent mean? Well, when you roll the die, that cannot possibly be affected by how the coin toss turned out. Whether we get heads or tails has no bearing on rolling the die, and vice versa. So these are independent events. And that would be a case where you could multiply the two probabilities taken separately to get the joint probability of A and B occurring. Now, this is a question of conditional probability. If the coin lands on heads, let's say you know that in advance. Now, what's the probability of event B, of getting that 5? To calculate this, just look at the first row, because now we know the coin landed on heads, and there are 6 possible outcomes in that first row. Only one of them is favorable. So the answer to this is 1/6. And what you should notice is that's just the probability of B, where we didn't know how the coin toss turned out. Well, that's what you would expect. Conditional probability shouldn't turn out any different than just the probability of B when A and B are independent events. I should say the coin toss and rolling the die are independent events. So here's the definition. A and B are said to be independent events if the outcome of one does not affect the probability of the other. And then when that's the case, as you saw above, you can compute this compound probability by multiplying the separate probabilities. So dependent events would be where one outcome depends on how the other one turned out. And we'll get an example of that in a minute. Now, here we're going to be drawing one marble out of a bag. In example 2, there's 7 marbles in a bag, 2 red, 2 blue, 3 green. Event A is when we draw a marble out, the first marble, it is blue. What's the probability of that? And the answer is there are 2 blues among 7 marbles. So that's pretty easy. Now, when we draw that blue marble or any marble out, we're going to put it back in the bag before we make the second draw. So the status of the bag for the second draw is exactly the same as what we saw for the first draw. There's 2 red, 2 blue, and 3 green. All the marbles are back in there. They're all scrambled. Each one is equally likely. So the probability that the second marble drawn is green is event B. Its probability is there's 3 green marbles labeled G1, G2, and G3 among 7 possibilities. So that's 3/7. Now we're going to look at a joint probability of A and B. In other words, we're interested in getting a blue marble on the first draw and a green marble on the second draw. Well, I've made a big array or chart of all the different possible combinations where we draw a marble, put it back, and then draw a second marble. So what does these symbols here mean? Well, B2 means that's a blue marble, the one labeled 2. G1 means that's the first of the 3 green marbles. So B2 G1 means I drew a blue and I drew a green. In particular, it was blue 2 and green 1. Whereas G2 R1 means my first draw was the green marble labeled number 2, followed by the red marble labeled number 1. Well, there are 49 different possible outcomes in this sample space. But if you want both A and B to occur, okay, then you have to get blue on the first draw. And that's, all of these here are blue on the first draw. And those are the only ones here that have blue on the first draw. And then you have to get green on the second draw. Well, that narrows it down to these 6. So the answer to this, the probability of A and B, is 6 out of 49. Now what was the probability of A? It was 2/7. What was the probability of B getting the green marble on the second draw? That was 3/7. And once again, we see that if you take those two probabilities separately and multiply them together, you get this. So this is another case of the probability of A and B is the probability of A times the probability of B. When can we do this? Well, when we know A and B are independent. And the 2 different drawings of marble from the bag, these are independent events because basically because we put the marble back in the bag after the first draw. And so the status of the bag for the second draw is no different. And so it's really the same situation. Now, what's the probability that the second marble is green when you know that the first marble is blue? That's a conditional probability, isn't it? So we know how the first draw turned out. It was a blue marble. Well, so what? We put it back. Okay, well, we're going to limit ourselves to these 14 possible outcomes. Remember, because we know the first marble is blue. And the ones that are favorable are these 6 right here. So the answer to this is 6 out of 14, which of course reduces to 3/7. But wasn't that the probability of event B, that the second marble drawn was green? The answer is yes. So it doesn't really matter what the first draw was, that it was blue or any other color, because when you get to the second draw, that's an independent event. Now this one's set up a little bit differently. You still have 7 marbles. You still have 2 red, 2 blue, and 3 green. But this time when you pull the first marble out, you're not going to put it back. So this is called drawing a marble without replacement. That has a big effect on the second draw. And we'll see how that works. Probability of getting a red marble on the second draw is either this or it's this. But I'm here to tell you there's no way to know which one it is. This is not a possible problem. We can narrow it down to 2 possibilities, but we can't determine which one's which. Now, why would it be 1/6? Well, if the first marble is red, then you're down to just 1 red marble. And a total of not 7, but 6, because remember we didn't put it back. So that would be 1/6. But if the first marble drawn is blue or green, let's just say maybe it's green. Okay, well now you still have 2 red marbles in the bag, but you took one of them out, one of the green ones, and so now you're down to 6 instead of 7, and that's how we get 2/6. But again, you can't know which one's right because we don't know how the first one turned out. So in event B, what's the probability the second marble is red? If you know that the first marble was red, okay, we've already discussed that, it's 1/6. Remember, because the first marble drawn was red and it's gone. It's not replaced. So now we have 1, 2, and 3. Only one of these is favorable. That's how you get 1/6. We've also discussed this one already, and it's 2/6. Because if the first marble is green, one of these is gone, and now you're down to 2 red, 2 blue, 2 green, a total of 6. So the probability of this is 2 out of 6. Event D, what's the probability that the first marble is red and that the second marble is red? So this would be drawing red marbles back to back, even though you didn't put the first red marble back in. Well, first of all, the sample space is not 49 anymore. It's down to 42. And that's because if you drew a red marble out, you couldn't draw that same red marble back out because you didn't put it back. But you could get the other red marble. If you drew green marble number 1 on your first draw, then you could get another green marble because there are 3 of them in there, but you couldn't get the same green marble. So these outcomes highlighted in yellow are removed from the sample space, and there's 7 of them that are now not possible, and 49 minus 7 is 42. But anyway, we can get what we want here, and there's 2 ways to do it. You can draw red marble number 1 followed by red marble number 2, or you can draw red marble 2 followed by red marble number 1. So there's 2 ways to get what we want. So the answer to this is the probability of event D is 2 out of 42, or 1 out of 21. So notes here at the bottom of the page. Conditional probability. The probability of an event A, knowing the outcome of event B, which is often read the probability of A given B, is symbolized like this. Probability of A slash B, A given B. And it doesn't really matter whether the events are independent or dependent. This can always be calculated like this. And I think the next example will illustrate that. So here's the idea. You're going to go and find the probability that both A and B occur and divide it by the probability of B to get this conditional probability. Now let's take a look at this example. There are 100 students at a summer camp where they get to do outdoor activities, swimming, hiking, arts and crafts, fishing, archery, whatever. We're going to look at 2 of these activities, hiking and archery. We're going to try to fill in this diagram. This is called a Venn diagram. That's set up for hiking and archery and for the whole camp, but no other activities. So be careful about grabbing numbers up here and trying to put them in. For example, it says, hey, 50 students liked hiking. I would not put a 50 here because you're going to have to break that 50 up into those who like hiking but not archery, versus those who liked hiking and archery. The way to start one of these Venn diagrams is try to find this region right here. The information for that is this. There are 7 kids who like both archery and hiking. You put them in, and that's how you start it. Now, how many kids like archery? 20. Okay, I've already accounted for 7 of them, so I put the other 13 here. These are kids who liked archery but didn't like hiking. Similarly, for hiking, we had 50 students total. I've already accounted for 7 of those. So what do we need? We need 43 more, and then you get your total of 50. Here are kids who liked hiking but did not like archery. Here are kids who like both hiking and archery. Now the total so far in this entire Venn diagram is 43 plus 7 is 50 plus, it's 63. You need 37 more to get to a total of 100. Now who are these 37 kids? They didn't like hiking. They didn't like archery either. And so this is correctly set up, and once you do this, this is a great way to figure out some probabilities. The first probability is, what's the probability that a student likes archery? And the answer is, we have 20 kids here in a camp of 100. So that's 20 out of 100, or 20%, or 0.2. How about hiking? Hiking was more popular. The probability that a randomly selected student liked hiking was 50 out of 100. And I think you could figure these two out without the Venn diagram. What about this? What's the probability the student does not like hiking? Well, one way to go about that would be to add these two together. Because these are kids who liked archery but not hiking. These are kids who did not like archery or hiking. And that accounts for everybody who did not like hiking. And that's 50. The other way to do it would just be to use a little logic and say, if 50% of the kids like hiking, then 50% of the kids did not like hiking. Now, probability of D. Both A and B occurring. What's the probability that there's students who like archery and hiking? Not very high. Probability of A and B is just these kids right here. Out of all 100 kids at the camp, that's 7 out of 100. What about the probability of A given B? Well, if you're given B, that means that you've drawn a student out and you already know that that student likes hiking. So we're talking about these 50 kids. So now there's a greater than the 7 out of 100 chance for this. Probability of A given B is written like this. And you just find all the kids who like hiking, and then make a fraction where you take the kids who like archery and write it like this. 7 out of 50. Another way to do that would have been to use the formula that we saw on the other page, where you take the probability of A and B and divide it by the probability of B. So the probability of A and B, what was that? That was 7 out of 100. And what was the probability of B? That was 50 out of 100. And sure enough, when you divide these, you'll get 7 out of 50. Okay, these last two examples have nothing to do with summer camp, or hiking, or archery either. We know that events A and B are independent. That's our assumption. We have a calculation for probability of B. We know the probability, the joint probability of A and B, but we want to know the probability of A. To solve this, just remember this formula. Probability of A and B for independent events is probability of A times the probability of B. Okay, there are 3 numbers here, and we know 2 of them. We know this one, for example, is 0.15. And over here, we don't know this one. That's the question. But we do know probability of B. And the probability of B was 0.5. So to solve this little equation, just divide both sides of it by 0.5. So you get 0.15 over 0.5 is the probability of A. And that turns out to be 0.3. That uses one of our important formulas for today for independent events. Okay, the other important formula we had today looks like this. The probability of B given A is sometimes best calculated as the probability of A and B divided by the probability of A. Now let's go look up some of these numbers. We know this conditional probability is 0.48. We know the probability of A is 0.2. What we're trying to find is this joint probability. And the way we're going to do that is multiply both sides of this equation times 0.2. So we'll get 0.48 times 0.2, and that makes 0.096. and that is the probability of A and B. And we're done. Hope you enjoyed this. Maybe you learned something. My name's Eric. Have a good day.